All right, welcome everyone. This is the AI Precision Health Affinity Group based at Honolulu, Hawaii. Today we're very excited to welcome Dr. Ulas Bagci from Northwestern University. He's an associate professor of the radiology department, but he also has courtesy appointments in electrical and computer engineering, biomedical engineering, and a courtesy appointment in computer science at the University of Central Florida. Dr. Bagci regularly serves as an area chair for PHI, which is probably the top AI for medical imaging conference, and is an associate editor at top journals in this field, including IEEE Transactions on Medical Imaging, Medical Physics, and Medical Imaging Analysis. We're very lucky to have him joining us today, and um, I just want to mention that the AI Precision Health Institute Affinity Group meets every month. We like to hear from leaders in the field of AI and healthcare. We try to bring together people from all over the world on these Zoom seminars, people with expertise in computer science, engineering, nutrition, epidemiology, radiology, and both, the researchers and the clinicians and advocates working in this field. The format is roughly a 30-40 minute talk. We like to leave some time for questions at the end because people usually have lots of questions for our speakers. And if you have feedback or suggested speakers, please email Dr. John Shepard, uh, who's the professor at the UH Cancer Center, or me in the computer science department, Peter Sadowski. We're based here at the University of Hawaii Cancer Center. This is in Honolulu, just a couple miles from Waikiki. The Artificial Intelligence Precision Health Institute is run by John Shepard at the Shepard Research Lab here at the Cancer Center. And by me, I'm associated with the Computer Science Department and the Hawaii Data Science Institute at UH Manoa. Today, we have a compensation for our speaker. It's this beer stein with an image of a surfing person on the engraving.
Very nice.
And with that, I will turn it over to Dr. Ulas Bagci.
Thank you very much. This is a very nice introduction. I'm really, it's my honor to be here. So do you see the screen? So do you see the full screen or presenter?
It's the presentation.
It looks good.
Looks good.
Looks good? Okay, the full presentation. And because I have this weird configuration, I'm still not able to understand. Okay, so today I'll try to give the journey that we start using particularly eye tracking system to make a human in the loop AI systems. By background, I'm a machine learning, deep learning person, and all my career actually I work on mostly medical imaging. And the title is coming from one of the our latest work, Eyes Don't Lie. We have done something very interesting, which I'm going to share towards the end of this presentation. How human recognition is, very strong, and you should carefully think about, these hybrid systems, especially nowadays. The AI belongs to everybody; it's everywhere, but it comes with lots of problems and the drawbacks as well. I'll try to show some really good things happening in our laboratory, so we have, as you can see, the laboratory name include the hybrid intelligence, which I believe that for many years that the human should be in the loop, for especially for high risk task, high risk the applications. There are different ways of doing this, and in this talk I'm gonna focus on mostly like the eye tracking as a way of collaborating with the computer. In my laboratory, actually, we try to develop really trustable and robust AI systems. So we have actually 3 steps we define, going into the trustworthy AI, especially in medicine and like high risk applications. We are developing new algorithms, which we try to make them robust. We are working on interpretable, explainable AI methods with causality and that, the radiologists, pathologists, the physician, and all stakeholders, including patients, should really see some reasons about those decisions. And this is also not completely independent, but we also include the expert in the loop systems. This includes the robustness, for example, of the algorithm. This can naturally give some interpretation into some of these algorithms as well. So today I'm gonna focus on these expert in the loop systems. And I'm sure, you all know because it's a cancer center, but for those people who didn't really see the radiology rooms, there's a dedicated light source there. Usually it is darkened environment, limited distractions, and what radiologists are doing actually visual search and reporting. And nowadays we see that lots of AI support is also there. During this, this is the environment we want to include the expert in the loop. So we want really real world experience, like real radiology room experience, instead of just laboratory environment. So we want to have this natural environment that we can get feedback from radiologists. So that is one of the reasons that we spend a lot of engineering years to build a real-time or nearly real-time and real radiology room experience. Actually, this requires a lot of engineering approach to integrate all the software and all these conditions into the eye tracking, the environment. So these are there is a visual, there is a the reporting part, the speech part, and there is also AI support. Nowadays, this is like for many of these cases, there is an AI support, which we are also considering that one in our analysis as well nowadays. So how, for example, radiologists, the experienced radiologists or the young radiologists are relying on AI. So is there any automation bias or not? So we try to also to focus on these these recent topics. So the core idea, like when we start this research, we got also really good feedback from Dr. Jeremy Wolf as well, and also field pioneers, how we can actually use doctors' gaze to teach AI to learn like high level information. So so the human eye, you all know actually, so the product of millions of years of evolution, it's coming, and there is a the human has this higher level of actually the recognition at the high level is much better than computer. And as for many years in AI and machine learning, the algorithms were struggling to understand this high level, and still I cannot really say there is a cognitive process there, but because of the data and other things, actually it becomes more actually, from the pattern recognition, it becomes more possible. So, our core idea was, so it's not only, teaching the AI to just what to see, like in terms of pattern recognition, can we also include like how to see, how experts see? So there are so many, the papers about this, the search mechanism and, the search styles and integration of them with this system. So one of our ideas was, can we create a true partnership, just not like a second opinion tool, but let's learn something from AI, as a radiologist or pathologist or clinician, but also teach AI how we get some of these for us actually easier, the patterns easier, easier things to grasp, but for computer it is difficult. So, here actually, as a radiologist or, you are looking for something for smaller, like in the CT scan, something, the smaller and maybe infinitely very deadly tumors. And so it's a nodule, right? For lung cancer screening example, actually this one. So, and, every day you do this a lot, hundreds of times a day. And then if you make a mistakes, like missing, that is deadly. So you are gonna miss, one of the nodules when the patient comes back in, after 6 months, 1 year, probably it's gonna, the growth. So here there is a little tiny nodule, and it may be, the easier to, to miss, this tumor by radiologists, right? Although they do this every day, and the visual search, the humans have also bias. So there is this really nice, the article in Radiographics actually explaining this, the bias in radiology from 2018. So many biases are there in radiology room. Why of misses and misinterpretations? Especially two of them were actually we got the involve a lot to understand actually why it is happening. One of them is like satisfaction of search. The other one is inattentional bias. There are many of them. Inattentional bias is something like missing the findings. This is hiding in plain sight. So you may look at it, but you may still not see it. I think Dr. Wolf has a really nice paper on this one. And then there is also another one, satisfaction of search. We see this a lot actually in screening paradigms. So once the radiologist finds some already, the tumor is there, so their vigilance is actually decreasing. Their awareness may be not, the super focus. So they may miss, some secondary search is necessary for some alternative methods are, the necessary to catch, this kind of error. There are many other biases is there. So here the conclusion of this is like, the radiologists are great, but they can really miss the tumor. So, some of you probably know this famous slide already. The human error remains a significant problem in detecting abnormalities. This is the lung cancer, the cases, the missing cases is missing cancer is something. Overdiagnosis is another problem, and I think this is kind of the satisfaction of search, or you just pay attention to this, the nodule. But in this famous study by, I think it's Jeremy Wolf's already here. So except him, probably you can also you are not gonna see maybe. So there is this hidden gorilla there. So I think it was his students that used in 2013 paper, like 20 out of 24 radiologists miss this gorilla when they look at this. So this is just one way of showing that this the radiologists are great, but they may actually miss things. Then the naturally we are thinking that for many years, like if AI can help, right? So the AI promise, the coming to this, like we were calling this now, in the past, computer-aided diagnosis is the secondary, like the second set of pair of eyes. And we were thinking there should be unbiased, perfect second pair of eyes if we can use AI like this, machine learning, to find those spots missed or the misinterpreted, and then this can behave like a safety net for the expert, for the radiologist. And when I use all this, the keywords, this is what DALI, send me. It is, I think it is. We are not there yet. As you can see, there are so many mistakes there. Is the cartoonize. So AI is, the great helping, but we also know that, it has a lot of problems. And for the medical component, as you can see here, there is, once we run one of the, the top AI algorithms with a certain threshold, we see lots of, the false positives. It cries wolf, right? This is what we call false positives. So many, there is one real cancer is there, but there is also like dozens of harmless, the shadow. So our experience is that radiologists don't want to, click these and say these are false positives. So we need to improve AIs, the recognition of this, the cancers places. This can be because of, for many years, I think that's why one of the reasons many of these algorithms didn't go to the radiology rooms, because, it has a lot of false positive and other problems it brings. Nowadays, it is better, but still we are not there. So, after all this, looking at, the human and AI, so we can say that AI is powerful. as we see, in our everyday life and in radiology room, but it is noisy. There are lots of mistakes still there, missing component. And we know that human experts are also brilliant, but they can be fallible. So we are when we start this project, like in 2016, we said that okay, let's create a true collaboration. So it's not just one is helping the another, but the synergistic, the help for each other. So human experts are good at the finding all those false positive and understand they are false positive, but they may miss tumor, and the machine learning can be trained to catch what doctors are missing. This is what we try to do. And so I was lucky to get one R1 grant in the near past. We call it actually a radiologist center for this grant because it is expert in the loop, and we applied this to the lung cancer screening, prostate cancer, and several other things. But main idea was for doing this for CT screening for the lung cancer. And the idea was, exactly what I said, that, let's create a true partnership with this. So that is, in eye tracking. So I just want to say, this is, the one actually cartoon representation of how eye tracking is, that in the screen you see the gaze maps, that where you look at it, and also this density is coming from how much, do you spend time there. When I was actually at NIH, actually in my the previous places, we used this Tobii Pro, the glass-based tracker at that time, and you see a CT scan here, and by the radiologists look at the certain parts, and you see this gaze map where they look at it, and density shows how much time they focus there. This was a good one, but as time goes on, more advanced eye tracking devices came. We used actually all of them in our research. Recently, we are using this iLink 1000 plus. The error rate is pretty low for this one. Alternatively, we are also trying to actually replicate our results with the simple, the low resolution webcam, because this device is very expensive. We have 3 of them, one in UPenn, one in NIH, and one in Northwestern. So we are actually working on like this, the cheaper options, if it is possible, if we can do it. Of course, there will be differences because of the error and all those things, but we still work on this. This is the journey of our laboratory for the eye tracking research within the AI. I will not have time to talk about EyeAssist and iTune, these very recent 2 works, but I will just very briefly say what is going on in our laboratory recently. So I want to start with the C-CAD. So when we developed this algorithm, like the true collaboration, we call this actually it was 2006 we started, but 3 years engineering effort to incorporate all this, the software and real time, the tracking and analysis, into the radiology room. So at that time, the jargon was computer-aided diagnosis system, and the C means collaborative. So we use the collaborative CAD. So how we started, actually, this is the simple system. We were using this glass-based system, and there was an eye tracker, which is, from PACS system. We were reading this, and it goes to our software and the real-time software, and then we put also some AI algorithm inside to analyze this gaze pattern along with the image itself. And there is already in the background some detection or segmentation code is working, and we try to actually incorporate this gaze information in a most engineering way to analyze the images and see if we can manage to do something with the human attention instead of the computer attention. One of the difficulties that I need to share, for those who want to actually do research in this field. So for the real radiology room experience, we wanted, so every hospital have different PACS system, and putting the PACS systems, this software and everything was very difficult. Putting the AI algorithm inside these, or that's really challenging. So we developed very simple PACS. ourselves, and that we integrated this to our eye tracking system. But we put all the availability of this, the mouse, keyboard, and other interactions of radiologists, so that we can actually capture everything. So, for example, in the laboratory environment, in different conditions, people are forced to fix their head and only 2D, and there is no really zoom and other things in many applications we have seen. So here, radiologists can change the contrast. They can go to other slices, and they can do some measurements. They can also speak, and we record everything. All this mouse, keyboard, voice, everything we record, and then we just need to start eye tracking and end eye tracking. The rest is the same as the screening. This can be done also in multi-screen as well. So we have done that. So what we noticed that actually, so usually these softwares, actually these eye tracking devices, give you a gaze map like this. It's like an attention map. So, and it is like a directed line. You have saccades and the fixation points. So for between each fixation points, you have this directed the search pattern. So we noticed that actually we can model this as a graph, because the fixation can be considered like a node, and then saccades can be considered like vertices of the edges of the graph. And let's directly use this instead of like putting smoothness and some this eye tracking, this device-based just this map. Let's use exactly these gaze patterns, and then integrate directly those values into the deep learning. This is how we started. So the gaze data, we start modeling the gaze data as a graph, and all the fixations were considered like a nodes, and the saccades were considered like the edges. So this was actually directed graphs, because there is a starting and end position. Well, once we actually start doing this graph, actually we noticed that this graph has a lot of nodes and repeated saccades, so many repeated positions. So it was very huge data at the end. This raw data is coming from CT scan. As you can see, lots of nodes and lots of the edges, and if you look at the B, this cluster data, so many of these edges are also repeated, because the radiologists go back to the same position, and also their eyes are actually moving. So the idea was actually, okay, we have this valuable data, but I think we need to just cluster them and just minimize it so that it can be used for the real time or nearly real time. First, we did this clustering. So when the radiologists look at one point, there are maybe hundreds of maybe even more points. We just need to use a few points. We don't need all these points. So that's why actually what we did actually very simple non-parametric clustering. It's a linear time. And then this way we are reducing the fixations. And the second one is the graph supersification, because of the saccades are repeated. So we find those repeated saccades and remove them from our system. We call it graph supersification. And that was actually also linear time algorithm actually we used. It was already available somewhere for some other purposes. People did actually, we just adapted to our the system. And here you see how we remove those systems. And at the end, actually, whatever left, we call it actually sparse, the attention map. So we include them into the CT scan as a prior attention map to focus on, these regions that, radiologists are looking. And then whatever your, the task is, in our case, it was like detect the nodule, segment it, and also, also characterize it, even like if it is, first of all, if it is an empty place or not, nodule, non-nodule. Segment it, and we also put like if it is cancer or not. That part was, even if it is cancer or not, still people go to biopsy, but the screening actually includes these measurements, so that we have done. When we start this, like CNN was very popular, so we have used CNN, and then in our laboratory we developed some other algorithms which were more robust and the less parametric. We used capsule algorithms. It was believed that it has more biological the root for this by Hinton And we developed this, the first ever, the segmentation version of capsules, and also the explainable capsule we have done. So when we find these nodules, we were also able to characterize by 6 attributes, visual attributes. The capsule didn't really fly, but it was working fine. Some, the RAM-based, the parameter-wise, it was efficient, but not really efficiency from the time. Time efficiency was not that great. So we also switched into, the transformers later on. So as you can see, this was published in Medical Image Analysis in 2019. It's a long paper. We have decided to actually switch into something actually more like end-to-end system. Before going into that, actually, I want to show, like, this is the, the radiologist, our first radiologist example, where they look at it. This is the dance pattern. And then if you look at this region, this scan was finished in 2 minutes, and that region, this red region, is showing only 8 seconds, the seconds, almost 9 seconds portion of that is there. After we apply our sparse attention mechanism, like removing, the saccades and, this fixations, we have only this parts left that we put them into do deep learning. And our second radiologist, third radiologist, we noticed that radiologists may have different, the attention maps. And this third one was actually I think it was first year radiologist. The first one was more experienced. They spend less time, 2 minutes compared to 5 minutes. And then, but at the end, still pretty sparse attention map we use. So we understand actually at that point that we can use these attention maps to personalize AI. So that is also possible. So for different radiologists, when you sit and look all those images, I think we can learn their the patterns, and if we can also learn their biases and other things, we can personalize the AI system to adapt it. So we are also, nowadays we are doing this with the LLM-based systems. But when we actually finish this study, we have done like the covered regions and uncovered regions. So the radiologists look some places and they may not really look other places. So we are able to understand with this graph, we can actually understand where they really look at it, and with some assumptions and some guessing, some parts based on actually the covered region. And you can see in these images on the corner, the red ones are the ones they didn't look at it. And then there is also this green one if they look at it. So at the end of the screening, actually, nowadays, we also show them, do you want to look at where you don't look at it? So it is like a second chance, actually, we give them, because we run the algorithm again, in especially those regions, they didn't look at it. If there is something missing like this, on the screen, so we show them actually there is something interesting. Do you think this is the nodule? Do you want to update your report? And this way, actually, we are with the second check, we are able to increase their the precision. So more than 2% sensitivity increased actually. We did actually with this the eye tracking based system. And almost 75% reduction in false alarms at the time. And so that was the the initial engineering study with the nearly real time, almost near real time working. And then when the SAM comes, the segment anything model comes, one of the first this foundational model segmenting anything. So this was just the beginning, like. We believe the C-CAD was it was a successful attempt to integrate the human attention there, and there is a potential way to do more actually on this. So it really opened our eyes to a much bigger idea. So we realized that actually we can use this eye for more than just finding the things, but we could also use it with interaction with AI in real time. So the easiest thing was like almost every CAD system starts the segmentation and measurements of the organ, tissues, tumors. So can we do this real-time interaction using the SAM or similar the SAM models? So we have done this real-time auto-segmentation of organs and tumors with GazePro. So the radiologists look at it, and then we just segment and the measure whatever the clinical need is there. So this was published in one of the workshops of NeurIPS in 2023, and the method is applicable to the other domains as well, not only medical imaging. And here on the left-hand side, the red one is like where the radiologists are looking at is, and the organs are segmented like this. This was the very early attempt. Currently, we are able to actually do something a little bit more, like you look at the tumor. If it is, it can segment 3 tumor type actually in our target now: liver, pancreas, and kidney. Once it is, you look at it, actually we are able to the segment, and maybe the radiologists want to look at some other parts. This is also possible. Here we just compare the inference time. If you use the with the mouse and SAM, it's almost double of this time. So it is pretty efficient, and we have seen that there is always a better way to integrate the such things. So going back into the C-CAD, almost everything was engineering and connected really nicely. But we were thinking, like, can we implement this eye-gaze graph directly on the deep learning? So because our graph was coming from C-CAD and from the fixation, and we built this, but there is an algorithm, there is a method called graphical neural network. So can we use this deep learning method and directly do everything on the graph, but on the deep learning? So just improvement on the C-CAD. So this is how our GazeGNN comes. So the GNN is graphical neural networks, and then we include the gaze information there. So we were not the first one to think about this, the putting the eye gaze patterns with the deep learning. So there is this attention consistency architecture. Here the eye gaze actually is considered like a supervision source. And the thing is, our experience with this method was like there in inference time there is no eye gaze data, so I cannot really talk about its robustness. Then the human is in many of our cases actually it's more robust, right? So the performance drop also when the testing data set is from the other domain, out of distribution domain. So there is actually 2-stream architecture, so we know that this is also available. So the image is analyzed from one encoder, eye gaze patterns, and this is visual attention map. One means visual attention map is also analyzed through another encoder, and these 2-stream architectures is concatenate these things, and it learns how to concatenate and then classify, and there is a prediction. But because of there are 2-stream architectures, so there is a drawback about the inference time. So what we came up with is actually we directly put the gaze embedding and the image embedding together without putting them separate encoder, but put it into the same encoder using the graphical neural networks. And this is we believe that it is robust and time efficient, and it was published in the WACV last year. And the idea was like we, similar to transformers, we have patches and we analyze all these patches from the gaze pattern. We are using the time aggregation, how much the time the radiologist spent, and we embed them with the images and then put the graph. We construct a graph, and based on this graph, actually we have done this X-ray analysis to see if we can really do diagnosis or not. And this time information, like the eye gaze information embedded into the images, is going to improve the diagnosis or not. So this is the details of the neural networks GNN that we use. I can go back to this slide if there's an interest. So we look at the X-ray, and there was actually 3 classes: normal, pneumonia, and also chronic heart failure. These was the cases that we wanted to do classification. GNN has a lot of actually. First of all, it really fits into our problem because of the first graph reconstruction of the gaze pattern. The other one is that for different nodes of the graph, we can it has a flexibility to represent different types of information. So that is one of the the good thing about the GNN. Even GNN itself has the better the performance compared to some of the other baseline transformers and GazeSam for this particular problem. as you can see there, you see it is one of the already, the really good ones. So we choose a really good baseline to start and then integrated later, our gaze patterns. We compared our results actually with some other gaze results that GazeGNN, actually this single architecture and two-stream architecture-based systems we compare. And we already have, the better robustness and also accuracy compared to those methods. I can also say with using, in our ablation, we show that actually when we use gaze information from human, these attentions are changing and we improve almost 3%, in the diagnostic accuracy. And it is pretty efficient compared to other two-stream and attention consistency, the architecture. The attention consistency, there is no gaze also inference time. So only two-stream, which is very actually slow. It is almost 10 seconds. I'm going to show how we get this 3% improvement, the visually. So these X-ray images, and in the right-hand side, you see the gaze pattern. And without gaze information, if you put them into the classification, so these red ones are showing this, it is a wrong prediction. And that is, the graph came without gaze interpretation. So when we include the gaze and do the classification again, and these misinterpreted images be classified correctly. As you can see, it was normal, now it is normal. So pneumonia, and attention is also changed. So the computer attention the computer was not really learning the correct patterns that the human inclusion improved the results. We can do many other things with eye tracking. I want to show this was with our clinical collaborator from Sloan Kettering. He was doing actually this segmentation by his eyes. The thing was at the time, like collecting images was very important, but drawing by hand was very challenging. So we included this segmentation algorithm, and he was just screening those images, and we were roughly segmenting. And the rough segmentation was enough for large-scale data collection, because later this rough segmentation were put it into a better refinement segmentation to improve the results. And as you can see, this is a really relaxed, the environment. He has even his, the coffee and everything, except, he can go other rooms or, to look at the other parts for a long time. We don't need to, to do calibration. Here you see the rough segmentations in CT, MRI, PET. So once the rough segmentations are done, actually, we just put all of them into the refinement to have some surrogate truth. The data collection purposes, we use eye tracking as well. Can we use for multiple screen? Yes. This is very earlier, the ways actually in 2015, but later, of course, we improved this. This was the glass-based system. There are 4 screens here for multi-parametric MRI cancer, prostate cancer screening. This was very interesting. I really like this study because, I can understand like which part of the images and which modality a radiologist look at more. And then how they switch into other modalities, like, they look at the T2 anatomical modalities here, and when necessary, they go to ADC, BAP, this diffusion modality, and they also go to the DC. Nowadays, big discussion in prostate screening, like if they need to use the DC or not. For example, I see in this case, radiologists often visited DC images as well to get some help, actually. So this also gives us, some idea about the multi-contrast, like multimodality, the learning of these images and in which sequence they go. Actually, this was very interesting for us. And here, at that time, actually, with our, again, clinical collaborators, he wanted to integrate before LLM becomes very, very popular. So he was using the speech recognition included in the eye tracking system, just the guide actually what he wants to do in terms of segmentation and the annotations. I'm gonna skip that one. We don't have much time. I just want to show also because so many things actually are ongoing and we are integrating them with AI. I want to show in GazeVal what we have done. So very recently, the one of the topic was this C-CAD open our eyes for many things, adaptation. And for difficult problems ongoing in medical imaging, can we really get more help from the expert radiologist? From this diagnostic part, we move into something. So this collecting the data is something, because for training the large scale deep learning, we really need the big data. And another thing to collect data is also synthetic images. It's very popular nowadays, and the CT, MRI, and all other things. And data augmentation is another one, but the synthetic images are very popular. And so we wanted to understand actually if those images are really realistic or not, and if we can really understand which parts of the images are not realistic, and if there is anything that we can improve. So we call it actually GazeVal. It's coming from the validation. So the idea was we think actually it is overly it's really overexcitement about the generative AI synthetic part of the medical images, especially. Probably in computer vision it is the much improved. So it's for foundational models, for many other things actually this is important. We are also using ourselves actually in our the laboratory a lot of synthetic data to robustify the systems and improve the accuracy and performance. And these are some of the really good and influential the studies from the literature, just like the MR physics base, the synthesize, and this is Nature Machine Intelligence, the article. This is for brain. I think it's still very cool, the very realistic images, and also like transformers for the reconstruction, the purposes. So an X-ray from Stanford, from Akshay's group, actually, they have also lots of the synthetic X-ray images, which were considered the amazing quality. So so we got actually these realistic synthetic images. So all these papers actually, when you look at them, they give numeric results like the similarity index, contrast, and some the local the parameters to explain the like fidelity and all these things. But from the the human perception, we didn't really see the significant works from the eye tracking. If I'm wrong, you can just let me know. So this one actually we try to understand actually how radiologists can understand and find those places which are not realistic. So we did 2 experiments for this, using eye tracking to identify the shortcomings of generative AI. Our main topic is that let's understand from human how they understand if something is fake from expert people, and then let's teach this to the computer to improve the the synthetic image generation. So that was our idea. So this is the beginning of how we start this experiment. So we asked them actually 2 tasks. In the first experiment, we asked the 16 radiologists from our department, without telling them actually if some of these images are fake. We asked them, can you just do normal screening and then tell us the diagnostic value, and we record all this. Only one of them actually really in the first experiment suspected, from the images, but 15 of them, they are all actually very well-known radiologists. They didn't really notice if this is a fake or not, and it comes into the again Professor Wolf's one of the paper. So it the attention is task oriented. So our task was diagnostic task. It was not a visual Turing task. After 3 weeks, actually, we asked them to come. And then this time, actually, we asked them, okay, the previously you did these diagnostic scans, but now the task is different. So can you just tell us if these images are real or fake? And actually, many of these, the X-ray images, of course, shuffled, and it is all blind to their evaluation. And then we noticed that actually all these radiologists, all of them, find the real and fake images with very high accuracy. So this is in the first experiment, the task was different. So we go back to this old theory, from perception, like this is task guided. We were more interested in actually. So let's see if they are gonna focus on some regions of the fake regions that we can learn and improve the generative AI. So that was, the purpose. So we use, this again, Stanford's original NeurIPS paper. They generate these beautiful images. It is the latent diffusion model, which one of the latest algorithms, stable diffusion algorithm. And you see, this, the X-ray, the images. We use 60 images, 30 generated, 30 real, and the ask 16 radiologists in deep varying, the level of expertise. If you ask them, this diagnostic one, the real fake classification ratio, actually, not the diagnostic, real fake, the classification. So similar, you see the real and the synthetic X-ray images, have similar accuracy here. And so the VTT means the visual Turing test. The time duration is, the less for when we ask the second question, if it is real fake, within 8 seconds they answer. When we ask the diagnostic question, of course, it takes longer time to, explore the images. And the visual Turing test for normal was actually, as expected, was, the higher accuracy of, the identifying. So the lower, because it's normal. When there is a pathology, the pathology may not look like very real. So that's why we have seen that, radiologists were, the better at, the capturing these things. So overall, actually, we ask later also verbally to, the confirm why you think that actually this is fake and this is real, and we also include them as a way of, the explaining. Because later we want to use all this attention mechanism plus these explanations to improve the synthetic image generation. We find really, the nice information there, like, when they say unrealistic bone anatomy, we see that actually this is overlapping with the second attention map. That is overlapping what they say. And then actually we record all those things, attention maps, and then working on now this diffusion algorithm to improve, like the human feedback is inside, and we are working on this to improve the synthetic image generation. Okay, so for this GazeVal, the conclusion was that human attention is task dependent. So when we asked diagnostics, so they didn't really focus on the fake real ones. And so we are now experimenting that, the human gaze patterns can improve, the synthetic image generation. We directly learn from humans' eye, expert people's eye. Instead of, having all these publications in the literature, so I can say we are not really there yet to beat the human in synthetic real fake, the separation. So the humans are very robust and strong, especially for this medical imaging. So I'm gonna actually, finish very quickly. So this is what we are doing currently in the lab, which we didn't publish, but still, actually, it is operational. We have this project called EyeSee, and there are also 2 more. Actually, experiments are finished. We have some really interesting results. So in EyeSee, actually, what is happening with AI is that now, the field go into the foundational model, or that's called the vision language models. So we are also switching into vision language model to make them more efficient, the radiology screening. So we have radiology reports, we have, the radiology images, and then that is, the large scale, the data, and we are trying to incorporate the gaze system. So this is what we call actually the EyeSee. So the current foundational models, like, now Google has, Microsoft has, and there is also, from Boston University, the Kai-Hans group has one, and, a few more. For X-ray, CT, and the more is coming from China group. Actually, there is also a few of them. So we are taking this foundational model, and we are now incorporating the human in the loop of this foundational model. We call it EyeSee. And so this is going to be like optional, because in some of the repeatable tasks, we understand that, the human attention probably is not really needed for this simple task. However, for more difficult tasks, as an option, we are actually learning from the gaze patterns, and we are trying to put them into the radiology report pretty easily. So using the report generation component of this vision language model and then updating this with the human attention, which is coming directly from gaze pattern. So this, we believe that the future is symbiotic. Experts should be in the loop for, as a safety net and to make things actually, especially for challenging tasks, easier. And more adaptation and more interaction can come. Eye tracking is one of them. And this was the very earliest version of actually what we were doing. And nowadays we are able to do with the speech. And also there is a report version. And it is like a chat box like GPT, similar to GPT. You can include the images, you just ask question. And then for the report, actually, we are able to incorporate, optionally, the gaze patterns as well. And so we have the CT version of this. We are working on the MRI. MR has more unique challenges. It's more difficult. And before concluding, I want to show just one thing, which is from the non-medical domain that we have done. We have a patent for this as well. So, all my life, actually, we have seen machine learning core components, and then try to transfer many of these algorithms from different fields, from computer vision, machine learning, but medical imaging has their unique difficulties. So this project, actually, it was the probably unique experience for me that first time, the civil engineering people got something from medical imaging, and then they use this UNet kind of segmentation, and also, our the unique interaction with the computer and the AI interaction to solve some of the problems in the civil engineering, like the crack detection. And then instead of eye tracking system, we use mixed reality headset here. I want to show actually this very simple system we integrated. So especially at that time, it was in Florida that I was in UCF. So the idea was there are so many actually the road and bridge inspection necessary and it's dangerous to go there and do measurements by hand. So we developed this algorithm so the person inspector actually can just look at the region. We consider this as a scan, and then all this pathology, this crack actually we consider them as a pathology. So detecting, and then we segment this pathology, and there is a report is coming there, and it's all. It's pretty, the efficient and easy way of actually doing this. And different kind of pathologies, I call it defects, like the spall and crack and all those things can be analyzed. And this was actually also commercialized. Okay, so that is really end of my, the talk about the journey, about, the gaze. For this, the ongoing 2 projects, I don't have much slides on this, but, it's very interesting. And I'm happy to discuss about what's happening. One project we have EyeSee, the other one is iTune. So, so far, actually, in our radiology room screening, the experience, we were asking radiologists to look at the images. However, radiologists look at the electronic health record too. They also look at the previous scans and radiology reports as well. So in EyeSee, actually, we are actually really replicating the multimodal AI, but this time, the human is in the center. Radiologists look at, this text, EHR data, and report, and previous scan. And actually, we are trying to look at all of them, not only one scan to understand where they look at it. And so this is kind of analogy to multimodal AI, like, the multiple modality data are inputted into the deep learning. And we noticed that actually, when we incorporated electronic health record or other data, their scan time is their search time is already reduced by half. And then this is what we are trying to now combine, like improve the AI decision with the other data where radiologists look at it, which parts. We can still process those data as well, but we want to understand actually how they combine those data. And the iTune is very simple, but also I think it is a nice analogy about like most of these deep learning algorithms are using the pre-processed images. They are all clean very well. So we have the out of distribution data, not very clean images or pre-processed. We show them to radiologists, and we show also the very nicely pre-processed and clean harmonized images to see how their attention actually changes. In both projects, actually, we see some improvement. especially the first eye assist. Actually, when we incorporated, some other modality, we noticed that their reading time reduced by half for one particular experiment, where we are asking the pulmonary embolism prognosis. So from 30 seconds to 15 seconds when we include the EHR data and some other patient information to the radiologist. So they process all these things in their mind and their attention change. We noticed that. So when we ask in the second experiment, when there is some EHR data is available, their attention changed to actually more vital organs, we notice, and that is also their time is, the efficiency, increase a lot. So we are thinking to integrate, the eye tracking with their natural environment where they use not only, the images, but all other information. So the attention should be revisited with not image attention only, but something more multimodality. So to conclude, the human eye, actually, this is how we started, is very, very helpful. So not only where, they look, also how they look and search. We are believing that the human should be in the loop and that we should really, the build AI system that is open to interaction and learn. At the same time, actually, it can also, the help radiologists for their blind spots and for others, the benefits. And so we, our group is focusing more in the algorithmic side, and we are improving the algorithms with the more help from the expert and learning from their expertise. And then we believe that there are so many actually ways to improve this. The more adaptation can come. Just a few steps. So many things actually can be said here, and many of them probably includes more hours to discuss. But what I see that like the increased integration, especially visual language model comes, electronic health records or other, the data, the doctors look at the things holistic way. I think we should also consider all of them integrated into the system. And for more effective collaboration, we are believing that AI can be personalized based on who is sitting there for radiologists. And so explainability, interpretability is a must. There is no unique definition of this for different tasks, different explainabilities that I think we should, define them as a guideline and then integrate them into the system. And then the real-time decision is very important. Like, we should really go, from the laboratory environment to the real rooms and then, to make this like, the actionable. And I just want to acknowledge, the grant that supported us. And then I have, these collaborators from Memorial University and IHU Penn, and we have a really big team in Northwestern Radiology. Thank you very much for listening.
Thank you very much, Dr. Bagci. Are there any burning questions?